Okay, so the last topic was even and odd functions. Okay, so it is especially the even functions are very easy to recognize by looking at them because the symmetry is right there in front of you. The second one is less obvious, especially when there is a break like this in it. So that takes some time to get used to. But the main thing is still the algebra, how algebraically to verify that the function is or is not one-to-one. Okay, do not expect a function to be, I'm sorry, not one-to-one, odd or even. Do not expect a function to be one or the other. It is likely to be neither one nor the other. A function just about any polynomial that you take, or any even quadratic polynomial. Think about it. If you have a quadratic polynomial, you a parabola. Okay, as long as you are shifting it up and down, it will remain even, right? So, but it's certainly not odd to begin with. And secondly, if you shift it away from the x-axis, it will definitely be neither. So that's still even, okay? But once you move it away, doesn't matter where. It is a quadratic polynomial, but it's neither odd nor even. So odd even means some particular location. To begin with, it has to be located particularly in a special way with respect to either the y-axis or with respect to the origin. Okay, so it is not as clearly even because of the symmetry, a mirror symmetry in the middle, but it's not odd. And once you move it anywhere to the left or to the right of the y-axis, it's not neither odd nor even. Okay. So this is the algebra that you see here is the key. What you need to learn about stuff is how to determine that the function is or not even or is not odd. Okay, so you plug in the values. The formulas are here. So these are the two formulas in these two boxes that you have to verify by substitution. So you substitute the so you have your function f, and it is a condition to be verified for a particular value f. Plug in value of negative x on the left, and you're supposed to, through algebraic manipulations, to convert that function into the original. Okay, that's what happened on the left over there. A similar thing happens with the odd, except you have an extra negative sign, but still you have to end up with the original function. Okay. So that probably will be on the next homework assigned today. Okay. So the next thing we need to address is certain algebra, and we'll do it still in this one sweep as we have done before, and that is I'm talking about roots. So there is a word for root as it stands for the roughly speaking the x-intercept of a polynomial is called a root, but this is roots. I'm talking about square root, cubic root, and so on. These are functions. So these are new functions. We make them very easily in one sweep, as I said, as simply the inverses. So they are inverses. Of the power functions. Okay, so x squared inverse square root of y equal x squared. Its inverse x equals square root of y is equal to x cubed. Inverse is x equal to cubic root of y. And so on and on. For each power, there's an inverse, and we're using the term nth root. As you can see, it is the same radical sign used for all of them. It is like a superscript. We use the number that stands for the degree of the root. So every time you see a root, the only thing to understand it is go backwards and just say it is the inverse of the corresponding power. So what is the meaning of the cubic root? It is the inverse of the cubic power. Okay, so in that manner we get dot dot dot. We get all the infinitely many roots from the infinitely many powers. Okay, so the trouble is once we take a look at the picture of the powers, we see that this is not entirely true. There is some work to be done. So these are the power functions of degrees from 1 to 6, and ignore the symmetry. Well, I guess we can say that the first row are these functions are odd, the second row are these are even. But from the point of view of inverses, what matters here is what? If we're looking for the inverses of these functions, what matters?
Their direction.
What?
Their direction.
Direction? What do you mean direction?
Like the even functions, whenever you have positive or like this, flip them upside down.
No, upside down. No, it's not. It's not about upside down. It is something else. What functions have inverses? What kind of functions have inverses? Well, maybe if I just go and try to find the inverses in one sweep, it will become clear. So I'll just remember how we do it. We rotate the graph about the diagonal. So I'm gonna, if I can just find this thing, here it is. That's what I'm gonna do. So I take this, copy, and then I'm gonna rotate it. First, I'm gonna rotate it 90 degrees clockwise, and then I'm gonna flip it. Okay, which way do I flip it? Vertical. This flip, is it? Yeah. Okay. Yeah. Okay. So these are supposed to be in the inverses. The numbers also, unfortunately, got inverted as well. So we have to match them carefully. But you can see that the problem that we're facing. What's the problem we're facing? So 6 power functions. I was supposed to discover the 6 inverses by flipping the graphs. What's happened? Look at the graphs. Look, the first graph. This is actually 6 degree. What's the problem with this graph? Well, when we face that problem, and in fact, if we go back to the second degree, this one, right now we're looking at, well, the problem is it's not a function, right? Well, why is it not a function? There's that negative branch, yes, but how do we know? There's a reference that we can make easily to refresh your memory how we discover functions that are not functions. So this is not a function because what? It violates what? The vertical line test, right? So two intersections. The vertical line test is not satisfied. This is not a graph. If we go backwards to the original one, what is being violated? It's the same straight line, except it is either vertical or horizontal, so it's the horizontal line test, also known as what? What's wrong with this function? Well, compare to those. What's the difference between the first row and the second row?
The second row is not 1 to 1.
That's right, not 1 to 1. So all of these three are not 1 to 1. They fail the horizontal line test, and then which means that they're not invertible. Not invertible means that there is no inverse to begin with. Okay, so what do we do? Remember what we do about it. If we encounter a function that's not invertible, such as x squared, with the one that we are right now facing, what do we do to find or make sense of its inverse? What do we do? The function is not 1 to 1. We need it to be 1 to 1 to find the inverse. So what do? We make it 1 to 1. Remember how? Just throw out half of it. As simple as that. So the one of the branches, usually the left, the negative branch, is thrown out, and then the other one becomes 1 to 1, and it is invertible then, and you invert it. Okay, so roughly speaking, this is what we do. We just discard this part, and that part. Okay, which makes it 1 to 1, and then if those parts are discarded here, the bottom parts, then we are okay, because now these are functions. The vertical line test is satisfied, and so up to this point, roughly, that's where it ends. It lies entirely above the x-axis or the y-axis. Okay, so you can see the advantage of these are all even powers. Even powers have this problem. The odd powers do not. The ones on the right, they're inverted. They were 1 to 1. They remain 1 to 1. They are invertible as such without this kind of dramatic change of the domain. That's what happens. Is literally what we do. Removing the branches is a kind of loose language of, you can say, we restrict the domain of the function. That's what happens. So we remove from the domain of the function becomes this. So this is the new domain. Similarly here, it is all positive, or from 0 to infinity, it becomes our new domain, like this. Okay, so if that's our choice, if we accomplish that, then we end up with a function is 1 to 1. It has the inverse. Okay, and so at once we have six inverses of those functions. They are roots. So let me just write what those roots are. So this, unfortunately, everything is in the wrong direction, but this one is the second, or is the usual square root. This is the fourth. This is simply, well, this is the same. This is just x. That's not right. This is, so if, let me mark this. So if this is y equal x squared, then over here I have y equals square root of x. Okay? If over here I have y equal x cubed, then over there I have, I did it again, I did it. X's and y's are appropriately written. So this is x equals square root of y. Okay, and this is x equal cubic root of y. Okay, and this is x equal fourth root of y. And so on, depending on the number. So if you see, you can still see 6 here. So this is x equals 6th degree root of y. And 5th. Okay, so at once you have all these degrees available. The very first one, you can guess what this one is, y equal x. Its inverse, what's the inverse of y equal x? X equal y, yes. Okay, so it's itself, pretty much. So it is the diagonal. So if you flip the diagonal around itself, it is the same diagonal, so nothing happens. So anyway, we have these four roots. To understand how do I compute how do I compute the, say, fifth root of a number? And the answer is, well, the short answer is use the inverse. So what is third root of 7? And the answer is simply, well, it is the value of the inverse of y equal x cubed. Okay, so at 7, at y equals 7. So that's the short answer, which is maybe very not very satisfying, but what's behind it is very simple. X equal cubic root of 7 when x cubed is equal to 7. Okay, so in other words, you need in order to find the cubic root or any kind of root of a number, you ultimately what you have to do is to solve an equation. That's the meaning of the inverse function. All the inverse function come from solving equations. We just imagine that, or that we have solved all the equations at the same time, and that creates a whole function rather than just one number at a time, as this suggests. But still, it's still that's how it works. If you are to evaluate the cubic root of 7, you need to solve the equation x cubed is equal to 7. It is the same thing. These two statements are exactly the same. That's the idea of the inverse function. So the original function equal to some number, you solve for x, and that the answer will be the inverse function. Okay, so that applies to every single function, and we are only making this. Where is that thing? These graphs on the right, is the point of them is just to show you that yes, we hypothetically we have all of these functions together. If we have the functions on the left, then we have the function on the right. At least we can imagine what they behave like. We know their graphs. We know what we can ask and answer all the questions that we have about these functions. For example, we can ask about the domains. We can ask about their ranges. We can ask about symmetry. So let's quickly answer those questions about these new functions. So let's see domains first. So as you can see, the odd domain, the domains of the even roots are the same, 0, infinity for all of them, right? So the only values of x allowed or of y allowed are 0, infinity. But for the odd roots, it is everything. So there are no restrictions this time. The same thing actually happens with the ranges. Okay, so domain is a non-negative number. The range is non-negative numbers too. That is for even powers, which also happen to be even functions. Originally, they were even functions. They are not anymore. So that's the second question. So the third question, domains, we have established a domain, so all of those, either half of the line including 0, or it is everything. Okay, same with ranges. The next question is about the symmetry, and and as you can see, everything is pretty much very clean and simple with the odd powers. Not only the odd powers, they also are odd functions. As you can see, the symmetry is still there. Right, that symmetry, the center of symmetry is still there. In the second column, in the right column of this table, you can just verify how you can either rotate it or you can do central symmetry point by point. Either way, you got a transformation of the curve into itself, and that indicates central symmetry. Central symmetry, so it's odd. So it's interesting that if you start with a function that is odd, you take its inverse, it's still odd. With the other one, it's not so clear-cut. You start with an even function. Do you end up with an even function? So the second row over there, we take even functions, we take their inverses. Is the result an even function? Is this an even function? Why would you say it's even? Let me show you where the x-axis is. This is the axis. So the symmetry, it's mirror symmetry about this axis. So we don't even have anything to the left of it. So the symmetry is not this symmetry. This is the symmetry for a function to be even. And the answer is no, because simply the domain, it does not allow that to happen to begin with, because there is no values to the right of the x-axis or y-axis of the axis of the outputs. So if we want symmetry with respect to that axis, the one that I drew, then we would have to have some stuff here, and we have nothing. So the function is they are not even anymore, because of we had to cut the domain. You cut the domain and you lose the symmetry, and it literally has no symmetry to speak of, because it does not become odd either. But that pretty much all we need to know about the roots as functions. So once again, trying not to go into algebra, that's just about to come, but rather trying to kind of think holistically, and what if you have a whole function, how do you produce new functions once again as a whole, rather than doing one value at a time. That's how you flip those graphs, and suddenly you have the graphs for a whole bunch of new functions. So let me show you. Okay, so that's what has happened. From 6 and on, obviously you have infinitely many power functions. Then you flip them all, and you have 6 roots. So powers here and roots there. They will still be split into odd and even. So here I have odd powers, and I have even powers, and they continue on behaving very similarly, right? So odd functions will still have odd powers will still have they will be 1-to-1, or they will be 1-to-1 onto. They will be odd. They will just be flat and flat in the middle. See how it happens? How it becomes flat and flat in the middle, but they then will be growing very steeply past away from the origin. Okay, with the even powers, what's going to be happening on and on? They will still have even functions. They have they are flat. They get flat and flatter at the bottom. Okay, and then steeper and steeper on the sides. Okay, so even more steeper than that, almost vertical. And then it similarly, those features will be reflected after we have flipped the graphs. So nothing. So oddness is preserved by the odd roots. What happens to the power? The even roots. They grow very fast initially, as you can see that at the top over there, and then kind of very, very frequently flattens out, even though it continues to grow. It is slowing down in comparison to x squared. Okay, so that's the all we need to know about the roots to begin with. But the question remains, and we're going to address it now or shortly, is how is the algebra? Is the algebra of a lot of things, of powers pretty much, and powers on the left already, and you might know that roots are also powers, algebraically speaking. You remember how roots are expressed as powers? Square root is what power? No. 1/2? 1/2, right? So that's what we're going to explore, treating roots as powers. They happen to be the reciprocals of the powers they come from. Okay, so so then this will be 1/2, 1/3, 1/4, 1/3, 1/4, and so on. The reciprocal of the powers. This is 1/4. Okay, So, but we start slightly, let's start from the very beginning with the business of powers. Well, in fact, way back. Well, they're all confusing about these meanings of what is the meaning of x 1/2 or 2x and stuff like that. So a lot of confusion about that. So I want to start at the very beginning and start with an analogy between what? Addition and multiplication. Okay, so they behave very similarly. Okay, what I mean is this what is repeated addition? Repeated addition is what?
You continually add the same number.
Yes, yes. There is a word for it. Really?
Multiplication.
It's called multiplication.
Okay.
It wasn't. The answer is multiplication. Yes. And by that we mean this: a plus a plus a n times is equal to a times n. It is literally an abbreviation. It is literally an abbreviation. It is a convention, if you like, a convention. This is a convention. Just instead of adding, at some point we decided let's abbreviate as much as possible and just replace with. You don't want to repeat it many times, especially if it's a large number, and just you put a dot in the middle between the two numbers. Okay. Okay. What is repeated multiplication? Okay, let me start writing. A times A times A times A. N times.
Power.
It is a power, yes. The answer is power. A n. Power, in other words, for it is exponentiation. We haven't seen the exponential function yet, but at this point we're not saying which one is the variable, which one is the parameter, so we are just talking about algebra. We're not speaking of functions right now. So as you can see, the similarity is well, very close. So one operation is being repeated, and we're looking for to put it in a more abbreviated form, and we do it once for addition, and then we do it in something else for multiplication. So instead of putting a dot between the two numbers, we put that numbers of repetitions of the number on the multiplication as a superscript. Okay. So now, with that established, it's a convention of abbreviation. What we go from here is we look at properties of this operation. Once again, remembering and keeping in mind that addition is nothing but multiplication is nothing but repeated addition. So, for example, if I have what is it? A plus A So if I have n times here, and I have m times here. Okay, so then we know that the abbreviation tells me that the first one is a times n, and the second one is n times a times m. Okay, so but if we start counting the number of times a appears, what do we get? So a appears n times, and then it appears m times. Altogether, it appears n plus m times. Which means that the whole thing is equal to what? According to our convention, it's equal to what? A appears n plus m times.
A to the power.
No, not the power, multiplied by,
Multiplied by n plus m.
n plus m. Okay, so nothing but counting, and you see what we have acquired here. These two are equal to each other. What? There is a name for it. Well, there might be many. The a was multiplied by n, and it was multiplied by m, and then we took a out, which is the word for it. No, it's a factor. We are factoring. Right? So, like I said, we start with nothing but the idea that multiplication is repeated addition, and then in that sense, that's how we establish factoring, by just counting the number of times that number appears. So if it appeared n times and then m times, then altogether it appears n plus m times, and it simply means multiplication of our number by a by n plus m. Right? So if you look at what's happening on the right, this should be seen as a familiar formula, which is you call it either factoring, you call it another word for it. It's factoring if you go this way, it's factoring. If you go upwards, what's the name for it? You might remember. It's called the distributive property. So you distribute a over n and m. You multiply a by n and you multiply a by m. Okay? But it's the same property. You just read it from left to right, from right to left, and it's the same thing. And once again, where does it come from? There's nothing weird or new about it. You just count the number of time a appears. Okay, so that's what we have on the left. Okay, so does this sound familiar? Okay, so now what we do now, we apply the same idea to the second column here, to multiplication. So we'll be looking at repeated multiplication. Okay, so everything is exactly the same. So I take a multiplied by itself, first n times, and then also m times. Okay, then altogether it is n plus m times. A appears, just like on the left, A appears n plus m times. The only difference is instead of having the summation sign, we have multiplication signs everywhere. Okay, but otherwise it's the same idea. We just count the number of times A appears. Doesn't matter, so it still appears n plus m times. So what remains is just to write these two things in these two different ways. So in the first parenthesis, we have a appearing n times, so it will be a to the nth power, multiplied by the second term, a to the mth power. What's at the bottom?
A to the power of n plus m.
That's right. Okay, so once again, it's nothing but counting the number of times this number a appears here. Unfortunately, there is no name for it. Unlike that property on the left, it has more than one name, but this one doesn't have a name. But it is a very necessary property if you are ever dealing with repeated multiplication. A powers or exponents. So if you want to say x squared times x cubed is equal to x to the fifth, that's something that is useful. Going to be useful a lot. Okay, so that is the beginning. The analogy is I hope helping to understand that there is nothing about it but repeating operations again and again, and it is the complexity is no more and no higher than on the left. So the two columns, the exact same thing is happening. So the second column about repeated multiplication is no harder than repeated addition. As long as it's entirely about counting the number of times all of these terms appear. Okay. The second one is repeated. Well, once again, repeat addition, but in a slightly different way. And that is like this: a plus a. Okay. So this appears n times. Let's repeat it m times. The whole thing is repeated m times. So it's the same string of numbers, but it appears m times. Okay, so then each of these rows is a times n, and the next one is a times n, and the dot, there are more of them, a times n. But on the other hand, how many a's do we have total in the whole thing? Each row has n, and there are m rows. So altogether, how many? I forgot to put a plus sign here. So we're adding these. So a appears n times, then it appears n times again, and that and keeps appearing for m times each. So how many? N in each row, m times.
Would it be a times n to the nth power?
No. It's think about it. It's just a table. It's a table like this with n columns and m rows. How many cells does the table have?
Is it n times n?
N times m, yes. So altogether it is n times m times, which means that the whole thing is equal to, so a appears n times m times, which means that the whole thing is a multiplied by n times m, right? Okay. So on one hand. On the other hand, if I start adding these, it's supposed to produce the same result. Okay, so this is it. So a times n plus a times n plus a times n m times. So this is still m times. Okay, so it produces multiplication by n times m. Okay, so it's still nothing but counting of the number of entries. Okay, it is more interesting if we take it now to multiplication. It looks slightly different, but the result will be the same. Once again, we will be counting. So each of these appears n times once again, and then we repeat that by multiplication again and again for m times. So this is m times. So altogether, then we have a appears n times m times. Okay, so so then the whole thing is equal to what?
N times n?
That's right. Okay, Now, what is that we have on the right? On the right, each of these is, this is a to the nth power. The next one is a to the nth power as well, and then n to the nth power. Okay, so in other words, we multiply a to the nth by itself m times. What's the other notation for it? A to the nth power multiplied by itself m times. So what you're looking at is repeated addition again. Repeated multiplication again, right? So an multiplied by an multiplied by n, it's the same exact numbers multiplied by itself, which means that it also expressed as a power. So it is an what? Parentheses m. So nth power is multiplied by itself m times, which means simply that it is an taken to the nth power. Okay? And indeed, then we're saying that these two things are equal to each other. Okay? The analogy with the, so this is what we're saying here. The one for multiplication, for addition, I didn't quite write it fully. It is actually a times n times m. That's what it is. That way, it is much simpler formula, like this. Okay. So once again, counting the number of a's, either they are connected by addition or they are connected with each other by multiplication. Doesn't matter. At the end of the time, it is a whole table of a's, and therefore the number of them will be n times m, and therefore either you multiply by n times m on the left, or you take it to the power of nth power. Okay? Okay, so then let's summarize what we've got. We have the definition of multiplication by and as well as power whenever that second number is a natural number. That's the problem that we're facing really right now is very small but significant. N is a natural number. Why? It has to be a natural number if we want to speak of how many times. How many times? You cannot say n unless it is a natural number. So even 0 does not fall into this category. Okay, so then it means that we don't have these functions yet. The function is defined. If we want a function, then we only multiply by n, which is a positive integer, 1, 2, 3, 4, and so on. Even and that's the next stage is how about what if n is equal to 0? That's probably the simplest step that we can make. So try n equals 0. So we try to expand the idea of multiplication as well as exponentiation. So these are the two over here, multiplication and exponentiation, or power, to numbers numbers n that are not necessarily positive integers anymore. So the simplest one to add to the list is 0. Okay, so try 0. There is no such thing as repeating a 0 times. I mean, you can see that a is not there, so you can say there 0 times a appears. But what if you cannot think of it as a number? So, but fortunately, we certainly can guess what it is. So a times n, a times 0 is 0. Okay, and then similarly, a to the 0th power. No, it's 1. It's 1. So why? The question becomes why this is these things make sense, even though the description, the repeated addition, repeated multiplication don't apply anymore. Well, the goal is we're gonna make sure that the rules, the two rules, still work. These two rules that we just looked at, let me 1 and 2. 1 and 2. So repeated addition as well as repeated multiplication produces these two rules. They don't have a special name. Actually, there is a name for that one left on the left. It's called associativity. And once again, there is really no good name for, because I don't know, for the ones on the right. Okay, so we introduce a new possibility, and we expand the applicability of the formula that we're looking at. N equal to 0 is now a possibility. So we got to make sure that our rules still apply, and they do. Okay, so that kind of weird definition, especially the one on the right. The one on the left, everybody knows that you multiply any number by 0, you have 0. The one on the right is questionable. Some would question why it might be 0 or might be equal to a or something like that. But it's easy to verify that indeed it should be chosen to be equal to 1, and you can why, so that the rules still work. Okay, so for example, let's take the first one. So say to the 4th power. Okay, so it is also so a repeated 4 times on one hand. On the other hand, I can write it as according to my formula, it is a0 plus 4. Okay, so well, because 4 is equal to 0 plus 4, so then I use the rule number 1, and it's supposed to be equal to a0 times a4. Right? So I'm applying rule 1 in order to confirm that it works. And as you can see, it does work. Well, I probably don't need this anymore. Okay, and then because a0 is 1, and this is equal to a4, and it is equal to a4. Okay, so imagine that instead of a0 power is equal to 1, I put any other number there. So that this over here would not have 1 but some other number. If it is 0 or a, it doesn't matter what it is, it's not gonna allow our theorem, our formula to work out anymore. Okay. Similarly for addition as well, but we're not gonna worry about that. So, and then the next one is fractional, what we started with. Those roots will come in now. How do we multiply by fractional fractions, as well as how do we take fractional powers?